Okay, so to prove this claim, let's first give an exercise here. Suppose alpha 1 to alpha n are algebraic over f. Show that the elements, so a product of negative powers of these alphas. So something of the form, the elements of this form, alpha 1 to some power a1, alpha 2 to some power a2, to alpha n to some power an. These elements, with the ai's greater than or equal to 0, these elements span f adjoint alpha 1 to alpha n over f. Okay, so if you've got algebraic elements alpha 1 to alpha, got elements alpha 1 to alpha n, which are algebraic over f, here the goal is to give a spanning set for f adjoint alpha 1 to alpha n as a vector space over f, and we're saying that the spanning set is given by considering by looking at the elements of the form, well, product of powers of these alpha i's, the negative powers of these alpha i's. So just try to prove this by induction. It's quite simple, and in your induction step, you have to think about basically think about the proof of the degree formula if you wish. That remember if you had field extensions f contained in k contained in L, f contained in k contained in L. If you take here's about the spanning set. If you look at the proof of the degree formula, you'll see the following. So f contained in k contained in L, then if you take if you have elements betas which span L over k, and you've got elements alphas which span k over f, then the product of alphas and betas, so alpha I beta j, those elements are going to span L over f. That was half of the proof of the degree formula, right? That was half of the proof of the degree formula. So that's what you're going to use, and you're going to do it by induction on n. Okay, good. So that's you have that result. And then using that, the claim is now quite clear. Right? So we're assuming that k is a splitting field of the polynomial f over n. And now, okay, so we've got the restriction now. The restriction to the set of roots of f map from the Galois group of k over f to the set of the group of permutations of, or the symmetric group on the set of roots of f, right? But now, okay, so now the proof of the claim, okay, so we assume that k is a splitting field of f over f, right? So let alpha 1 to alpha n be the roots of f in k. Then k is equal to f adjoint alpha 1 to alpha n. And now by the exercise, any element, so by the exercise, any sigma in the Galois group of k over f is determined by sigma by the elements so it's by the following elements. Look, so sigma is the moment of the Galois group of K over F, right? So it fixes F, and now remember one of the previous videos we observed that when you say you have an automorphism of K which fixes F, that's the same thing as saying that this is an F linear. It's an automorphism of K which is F linear. So now, well, remember from linear algebra, if you have a linear transformation, the linear transformation is determined by where it sends a spanning set of the domain, right? If you know where it sends a spanning set, then you know the map. Now here, so your element of the Galois group of K over F, because it fixes F, it's determined by where it sends a spanning set of K over F, right? But a spanning set of K over F by this exercise is a set of monomials of this form. So by the elements of the form sigma, or by the elements, let's just say by the elements, sigma alpha 1 to the power of some a1, alpha 2 a2, alpha n an. These all a's being negative integers. So sigma, because it's F linear, it's determined by where it sends these elements, because these elements span K over F. And then these elements, because sigma is the ring homomorphism, in turn are determined by sigma of alpha 1 to sigma of alpha n. These elements, the latter elements, are in turn determined by sigma of alpha 1 to sigma of alpha n. So sigma is determined by sigma of alpha 1 to sigma of alpha n. So sigma is determined by what? When these alphas were instead of roots of f, right? Sigma is actually determined by how it permutes the roots of f. It's determined by where it sends each root of f, as we had claimed.